Hello. In this video, I will introduce related rates, word problem, calculus one. Um, and I will go over go over the steps related to related rates problems. And I will do 3 examples of related rates problems. So if you're doing calculus, you're going to have to do related rates. And related rates are basically a reason why we had to learn derivatives. You can actually apply derivatives um, in word problems or related rates. So what is related rates? Related rates just means just take the derivative in respect to time. That's all it is. So yeah, just take the derivative in respect to time. So your goal is to find the rate of change of 2 or more related variables that are changing with respect to time. So it's always in respect to time. So usually you take the derivative implicitly. Um, if you need to review implicit differentiation, go ahead and check out my video on implicit differentiation. And every variable gets multiplied by d over dt, or basically you just have to take the derivative in respect to time. So here's some very important keywords when doing related rate word problems. Rate or fast or speed, think derivative. So whenever you hear the word rate or the speed or fast, it's first derivative, right? And a derivative is always a constant. Increasing means positive, decreasing means negative, cubic means volume. Okay, so how do you solve related rates problem? I'm not gonna lie, these are not easy to do. You uh, because these are word problems. So what you want to do is here are some maybe like some steps that can help. Read the problem carefully. If you have to read it more than once, do so. And write down all the given information, even if you don't think it's important, write it down anyway. Okay, so read the problem carefully, write down what you have, write down any formulas that might be related to your problem. Then what I would do is draw the best image you can. The more detailed image, the better. So then step 3, find an equation that relates to the unknown variable and known variable by looking for geometric shapes known as formulas, ratio, Pythagorean theorem, area, volume, formulas, trig identities. So if they're asked talking about um, area of a triangle or a circle, write that down because you're going to need it. Uh, yeah, if they talk about volume, write down the volume of whatever they're given. Sometimes they might give you a cylinder, find out what the volume of cylinder is. Yeah, and use trig identities. So just make sure to keep track of the unit. So yes, very important. Make sure you keep track of the units. If they give you like a speed, make sure those units don't go away. Okay. Step 4, simplify using appropriate substitution so that the chosen equation has only 2 variables, known and unknown. So how this works is once you have, okay, so if they're talking about area of a triangle, right? You're going to take the implicit derivation of that. What you have to know is if you have 2 variables, you have 1 rate. So for example, area of they might give, the word problem might require the area of a circle, which is area equals pi r square. And you'll have 2 variables. The area is a variable, the r is a variable. So you have 2 variables, that means you're going to have 1 rate. If you have 3 variables, you're going to have 2 rates. So basically, if you have 4 variables, you're going to have 3 rates, etc. So basically, it's the number of variables minus 1, which will give you your rate, right? So if you have 2 variables, 2 minus 1 is 1. That means you have 1 rate. If you have 3 variables, 3 minus 1 gives you 2 rates. Okay, so that's how it works. Step 5, differentiate the equation implicitly or in respect to time. Substitute all known values into the derivative and solve for a final answer. Okay, so this means this is like a lot, right? So let's do a simple example and then let's do this step by step. So let's look for example 1. Example 1 says a pebble is dropped into a calm pond, causing ripples to form the shape of concentric circles. So the radius of the outer ripple is increasing at a constant rate. So rate is a speed of 1 foot per second. So that is like your first derivative. When the radius is 4 feet, at what rate? So what rate is a speed? Is the total area of the disturbed water changing? Okay, so if you have to read this problem one more time, that's fine. I'm going to read the problem one more time because however it takes. A pebble is dropped into a calm pond. So you drop a pebble on a calm and it causes ripples or ripples. So what does that look like? Let's draw that image. So let's look at the first piece of information. A pebble is dropped into a calm pond, causing ripples to form the shape of concentric circles. What is? Let's draw that image. So here you have a pebble, and it's dropped in a pond, and it makes waves or ripples. Just like that. Okay. So first step, I drew the image. I drew this piece of information. So a pebble, yeah. Then they're saying that the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So 1 foot per second. So we know that rate is first derivative. It's also a constant. So let's write that down. So we know that the rate is derivative. And then they're saying that the derivative of the radius is 1 feet per second. So if we take it in respect to time, that would be dr dt is equal to, it's growing, so it's going to be positive 1 feet per second. Okay. And then they tell us the radius is 4 feet. Okay, so make sure you have your units. So, okay, so we have a constant rate of 1 foot per second when the radius is 4 feet. At what rate? So we got to find the first derivative again. So a rate is a speed, is the total area of the distributed. What is the rate of the total area of the disturbed water changing? So area. So what is this area of? Is this, so we're talking about radius and we have the area. What does this look like to you? This almost looks like a circle, right? A circle, it has a radius. So what is the area of the circles? Area of the circle is pi r squared, right? So that is our first equation. And then you got it. So from this equation, can you tell me how many variables? How many variables do we have? So A is a variable, pi is not a variable, it is a constant. It's like 3.14. R is a variable, so we have 2 variables. So what does that mean? We're supposed to have 1 rate, right? 1 rate, because it's your rate is is your total variables minus 1. So if we have 2 variables, subtract that by 1, you have 1 rate. Okay. Okay, we have an image, we have an equation, we have a speed, a dr dt, we have a radius that's 4 feet. Now what do I do next? From the formula we have, a equals pi r squared, take the derivative implicitly in respect to time. So let's start with the left side. I know that the derivative of a or x or v is 1, right? And then if we're taking this in respect to time, this would be dA dt, right? What we have is on the top, and on the bottom is what we're taking the derivative in respect of. We're taking it in respect to time. Okay, so on the left side, it's 1 dA dt. Now, how do you take, on the right side, we have pi r squared. How do I take that derivative in respect to time? Well, you're going to use power rule, right? Pi is not a letter, it's a constant. Pi is about 3.14, right? So you have to apply the power rule. So it's this power times the coefficient. So that would be 2 pi. And then the r stays the same. And then what would be our new power? Our new power is going to be old minus 1. So 2 minus 1 is 1, right? You're just applying power rule. Now, we do have to take this in respect to time. So what do we have to add? We have to add dr, because that's what we have, our variables are, and then over dt. Okay. So what do we have? We can plug in, what do we have and what are we trying to solve? We have a dr dt. Good. So we can replace dr dt with 1 feet per second. What are we trying to solve? They're saying, what is the rate? So we're trying to find the speed. So I'm assuming we're going to have to find the only speed we have, or the rate, is dA dt. So I think we just have to solve for dA dt by given what we have. So on the left side, it's fine. One, you don't really have to include this one, so you don't have to get rid of anything. It's just dA dt. And then it's 2 times pi times r times dr dt. So it's going to be 2 times pi times r. Now, do we have a radius? Yes, we do. It is 4 feet. And make sure you keep the units, because our units are very important. So 4, and then don't forget you have feet, times dr dt. So dr dt is a speed. Do we have a speed? Yes. Our first derivative, it is yes, 1 feet per second. So make sure you keep the unit. So it's 1 feet per second. Okay. So if we kind of clean this up, put it all together, it's 2 times pi times 4. That is, I guess you could say 8 pi. And then we saw the speed here and this feet on the top. So that's going to be feet squared. And then on the bottom, we're still left with a second. Okay, so our speed, or our dA dt, is 8 pi feet squared per second. Okay, so we just solved this related rate word problem. So what I did was I drew the best image I could, write down everything I have, right? Write down everything I have. Radius is 4 feet. The speed, dr dt, is 1 feet per second. This represents a circle, so we have to use the area of a circle, which is a equals pi r squared. Figure out how much variables do we have. We have 2 variables, so that means we should have 1 rate. Okay, and then figure out what we need to solve. We need to solve for dA dt. Okay, so that was example 1. Let's move on to example 2. Air is being pumped So in example 2, air is being pumped into a spherical balloon at a rate of 9/2, 9/2 cubic inches per minute. Find the rate of change of the radius. So find the rate of change. So that means we have to find the speed. Find the rate of change of the radius when the radius is 2 inches. So we're probably gonna have to find dr dt, right? So first, let's do all the best image you can think of. So here we have a balloon. When you blow air in a balloon, it expands, it gets bigger, right? So let's try to draw a balloon. And they said the radius, so we have a radius, so we're probably going to be using the formula of a circle or a sphere. Okay, so here's the balloon, has a radius, and you're pumping air inside that balloon, it's getting larger, right? Okay, so here's the best image I can draw. Here's a balloon. There's a circle and a sphere. So let's write down everything we know about this word problem. So an air is being pumped in a spherical balloon at a rate of 9/2 cubic inches per minute. So that is our speed. That would be our dv dt. And that would be 9/2 cubic inches per minute. So cubic is the same thing as inches cubed per minute. So keep our units, we need our units. It doesn't go away. Find the rate of change. So that is a speed or first derivative, or in our case, I think that would be dr dt. Let's find the rate of change. So we're taking the derivative in respect to time. So we got to find dr dt. And then they tell us the radius is 2 inches. That's important too. Radius is 2 inches. Okay. Now, what kind of formula are we going to develop? Well, we said this is a sphere, right? A sphere. So what is the volume? Oh, and also, what else do they tell us? There's one piece of information that's very important, cubic inches. So if you go back to our notes, cubic is related to volume. So that's why we didn't use the area of a circle, because we have this cubic. So it's related to a volume. So a volume of a circle or a volume of a sphere. What is the volume of a sphere? It is V equals 4/3 I R cubed. Okay, so that's it. We need this formula. How much variables do we have in this equation right here? V is a variable, R is a variable, 4/3 pi is not a variable, it's a constant. So we have two variables. That means we must have one rate or one derivative, one rate. And that's true, we do have one rate. dv dt is 9/2 inches cubed per minute. Okay, then what I'm going to do is take the derivative implicitly in respect to time. So let's do the left side. What is the derivative of v in respect to time? So it's, the derivative of v is just 1, but in respect to time, you do have to add this dv dt. Okay. On the right, how do you take the derivative of 4/3 pi r cubed in respect to time? Well, first, I would definitely apply the power rule. So 4/3 pi, they're all a constant. So just multiply 4/3 times 3. And you'll see that the 3's cancel. So you're just left with 4 pi. And then r stays there. And then what is my new power? Basically, it's old minus 1. So 3 minus 1 is 2. Okay. Since we're taking it implicitly in respect to time, you do have to add the dr dt. So now you ask yourself, what are we trying to solve? Well, we have a dV/dt, which is 9.5 inches cubed per minute. So we're probably most likely going to solve for dr dt. Okay, so we got to solve for dr dt. And maybe before getting rid of this 4 pi r square, I think we can kind of clean this up. We know that the radius is 2 inches, so let's do that. 4 pi, and then my radius is 2 inches square times dr dt. I guess if you kind of clean this up, 2 square is 4, times it by 4, that's 16, and then you still have that pi, right? And times it by dr dt. And then, oh, what am I missing? I'm probably missing my units. Yeah, that's important. Let me erase this. Because the units doesn't go away. So what units were we using? Well, we said that our radius was 2 inches, but we had to square it. So if you're squaring an inch, you get inches square, right? So this would be, right? So this is inches. Inches square would be, I mean, when you square an inch, that would be inches square. So this was going to be 16 pi inches square times dr dt. And then over here we have 1 dV/dt. So we know that dV/dt is inches cubed per minute. So you're going to replace this dV/dt with 9/2 inches cubed per minute. Okay, now we have to solve for dr dt. So I have to basically get rid of this whole thing, 16 pi inches square. How would I do so? I guess I would just divide it by itself, right? That's the only way we'll get rid of it. So divide both sides by 16 pi inches square. This cancels, so you're just left with dr dt. Now this is confusing. You're going to have a complex fraction, and just be careful with the units. So if you want, so we have a complex fraction. This is your numerator, and then this is your denominator. So you could, if you want, you can rewrite this as 9 inches cubed over 2 minutes divided by 16 pi inches square over 1. Okay, and then how do you divide this? You cross multiply. So what's 1 times 9 inches cubed? That is 9 inches cubed. And then what's 2 minutes times 16 pi inches square? Well, 2 times 16 is 32. Yeah, 16 times 2 is 32, and then you still have this pi. You still have this inch square. And then you still have this minute. Right? Uh, okay, so so my final answer will be dr dt. So yeah, our final answer will be 9 inches cubed over 32 pi minutes. I kind of messed, I don't know what I did, but radius is 2 inches. Because they're asking find the rate of change of the radius when the radius is 2 inches. Find the rate. Yeah, so rate of change is yeah, this is right. I was confused. I wait. So we have 32 pi inches square per minute. So our unit is going to be, so this is going to be 32 pi inches square per minute. And then I guess the inches cubed goes away. So it's just 9 inch. And then you have 32 pi. So you see the inch cube over inch square that just cancels, just becomes inch, and then you have minute. So that is your dRdt. Okay, so that is very important. Keep your units. You might get marked off if your units are not correct. Okay, so that was example 2. Let's move on to example 3. So example 3 says all edges of the cube are expanding at a rate of 3 meters per second. So that's definitely a first derivative or speed. How fast is the volume changing when each edge is 10 meters? So volume, and we're dealing with the cube, so volume of the cube is length times width times height. So let's first start with an image. So all edges of the cube are expanding at a rate of 3 meters per second. So let's draw a cube. I'll try my best to make perfect cube. No, it's not perfect. Yeah, I tried my best. So, but this is not the perfect cube, but it is a cube. We have x, 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 or you could say side, 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 or y times y times y. It doesn't matter. All edges of a cube are expanding at a rate of 3 meters per second. All edges of a cube are expanding at a rate of 3 meters per second. So what does this mean? 3 meters per second. That is, I believe that's a speed. So this would be dx dt. And it's increasing, so that's positive 3 meters per second. So I'm gonna still keep my units 3 meters per second. And we know that what is it? Each edge is 10 meters. So x is 10 meters. How fast is the volume? So they're asking for a volume of the cube. What is the volume of cube? It is, or volume of anything. Volume of a cube is length times width times height. So our volume of a cube is each length is x, so x times x times x is x cubed. Okay, so based on this equation, v equals x cubed, how many variables do we have? Well, v is a variable, x is a variable, so we have 2 variables. That means we have to have 1 rate. Okay, so the next step I would do is take the derivative of v equals x cubed implicitly in respect to time. So start with the left. What is the derivative of volume in respect to time? Well, the derivative of v is 1, but in respect to time, you do have to add that dv dt. On the right, what is the derivative of x cubed in respect to time? You apply power rule. So this has a coefficient of 1, so 1 times 3 is 3. And then this is x cubed. I mean, not x cubed. No, it's all power minus 1, so 3 minus 1 is 2. And then you have to add the dx dt. Okay, we are given dx dt, so that means we're probably going to most likely how fast is the volume. How fast is the volume changing? So we're going to probably solve for dv dt. Okay, so it's kind of solved already. We have the left side 1 times dv dt, so you don't have to get rid of anything. So you could say dv dt is equal to 3 times x squared times dx over dt. So 3, and then we said our x is 10 meters. 10 meters. And then we have to square that times dx dt, which is 3 meters per second. Okay. So it's going to be dv dt. 10 meters square. What is 10 meters square? Well, 10 square is 100. And then you also have to square the units. So what's meter square? Meter square. Times it by 3 meters. And then over all over second. Okay, so dv dt is, well, what's 3 times 100 times 3? That would be 900. And then what is meters squared times an extra meter? That is meters cubed. Over second. Okay, so that is our answer. dv dt is 900 meters cubed per second. Okay, so that is our answer for example 3. So you kind of get the hang of it. Read the problems more than once. Draw the best image. Write down everything what you are given and try to figure out what you are trying to solve. Find a formula that is related to your problem. So in our case, this would be volume. Take the derivative implicitly, try to find for your unknown, figure out how many variables you have that will determine how much rate you need or should have, and just try to solve for your unknown. And that is related rates. Okay, so this wraps it up for this video.